Right. Hey there, future data scientists. You know you're on the path to becoming a data scientist, right?
Yeah.
That's pretty awesome. But sometimes it can be a little overwhelming with just how much there is to learn in data science.
Yeah, absolutely. And it's such a big field and constantly evolving. But the good news is you don't need to get a PhD or something to be able to understand these really important core concepts.
Exactly. We're here to break it all down into little pieces, kind of like, a data pizza. We'll
Yeah,
point out the tasty toppings that always seem to come up in those data science interviews.
I like that, a data pizza.
Yeah.
One thing that might surprise you is that machine learning models, they don't always have to work alone.
Oh, really? They can team up.
Yeah, we call it model interaction. And there are some pretty cool techniques that allow these models to share knowledge and learn from each other. Like, for example, transfer learning. You can think about it like this. Imagine you are trying to learn Italian, but you already know Spanish. Chances are learning Italian is going to be a little bit easier for you,
Oh,
right?
yeah.
Because you can transfer some of that knowledge.
So the model has a head start. It doesn't have to learn everything from scratch.
Exactly. And this can be super helpful, especially if you don't have a ton of data for a specific task. You can actually leverage a model that's already been trained on a similar task, and it can boost performance. And you might be asked about this in an interview. They might ask you when you'd use transfer learning or, what kind of pre-trained models would you consider?
That makes sense. Like a shortcut in the data maze.
Yeah.
Now, what about multitask learning? So does that mean the model can juggle multiple things at the same time?
Yeah, precisely. In multitask learning, a single model learns to do multiple tasks all at the same time. So think about a model that's learning to identify both cats and dogs, but in the same image. And what's really cool is that these models can actually adjust their focus while they're training, based on which task is a little bit trickier. So the model is kind of saying, okay, I'm having a tough time telling the difference between these two different dog breeds, so I'm going to spend a little extra time studying those.
Wow, that is so smart. It's like the model has its own little study plan,
Yeah.
figuring out where it needs to focus its energy.
Mm.
Now, how would this come up in an interview?
An interviewer might ask you to compare multitask learning and transfer learning and really highlight the key differences and, when would you choose one over the other? And they might also ask you to explain how the model adjusts its focus. That's where understanding dynamic task weighting becomes really, really important.
So it's not just knowing the definition, but it's like understanding the why.
Exactly.
That makes a lot of sense.
Yeah.
Okay, what about active learning? Does that mean that the model is actively seeking out information?
Yeah, you got it. So active learning is all about making that model an active participant in the learning process. So instead of passively receiving data, the model can actually choose which data points it wants to learn from next. So it's like the model saying, hey, I'm a little confused about this particular type of cat. Can you show me some more examples?
Oh, that's so clever. So
Yeah.
it's like raising its hand in class, being like, I need some extra help.
Exactly.
I bet interviewers love to ask about that.
Absolutely. Interviewers might ask you to explain how it works, what are the benefits, and what are some of the different strategies for selecting those data points. It's a great topic to demonstrate that you really understand how models can interact with data.
That's awesome. Active learning, I love it. Okay, now for the last model interaction technique, federated learning.
Okay.
What is that all about? That one sounds kind of futuristic.
Yeah, it's a cool one. Federated learning is all about training models, but on decentralized data. So imagine you have all these smartphones, right? And they all have their own personal data. Instead of sending all that data to a central server to do the training, federated learning actually allows you to train the model directly on the device, but without sharing the raw data.
Oh, so it's like the model is traveling to those different devices to learn.
In a way, yeah. So the model parameters are shared between the devices, but the data itself stays put.
Okay.
This is great for privacy, and it's super helpful in situations where that data is just spread out across different locations.
Okay, so the data, it's like the model travels to these devices, gets the knowledge, and then just brings back the knowledge, but not the data. That's so cool.
Exactly.
I can see why interviewers would be interested in that.
Yeah, they might ask about the benefits, the challenges that are involved, and how it compares to traditional centralized approaches. It's a hot topic, especially when we're talking about data privacy.
Yeah, federated learning definitely seems like a game changer. So we've covered 4 different ways that models can interact. We talked about transfer learning, multitask, active learning, and federated learning. So many social skills.
Exactly. And these are all techniques that are becoming more and more important in the real world, so understanding them will give you a real edge.
Now, I know that models can sometimes hit a wall during training. So is there a way to give them a little boost? Kind of like a personal trainer for machine learning?
Yeah, you're thinking about optimization techniques.
Okay.
So it's like having a coach to help your model reach its full potential. And there are some really popular ones like momentum optimization, mixed precision training, gradient accumulation, and gradient checkpointing.
Okay, those sound a little intimidating. Can you break those down?
Yeah, of course. So imagine you are rolling a ball down a hill.
Okay.
Sometimes that ball gets stuck in these little valleys, right?
Yeah.
Momentum optimization is like giving that ball an extra push,
Yeah.
helping it reach the bottom faster.
So it's like helping the model find the best solution faster, avoiding those little traps.
Exactly. And in an interview setting, they might ask you to explain how momentum works or why it's beneficial compared to just standard gradient descent.
Got it. Okay, so momentum gives our model a little nudge. Now, what about mixed precision training? Does that mean we're like mixing things up?
You could say that.
Well,
So mixed precision training is basically a way of using different levels of numerical precision during training. You can think of it like using different paintbrushes for the finer details and then bigger brushes for those broader strokes.
okay.
And it can speed up training, especially when you are working with those powerful GPUs.
So it's all about using our computing resources in a smart way
Exactly.
without sacrificing accuracy.
But
Bet interviewers like to hear that.
they do. They might ask you about the benefits, the potential drawbacks, and how you might actually implement it in the real world.
Okay, so mixed precision training. That's like a data science efficiency hack. Love it. What about gradient accumulation? Kind of sounds like we're accumulating gradients.
Yeah, you're on the right track. So gradient accumulation, it's super helpful when you're working with like limited memory. It allows you to basically simulate training with larger batch sizes, which can be really good for the model's performance, but can also require a lot more memory. So gradient accumulation lets you get the benefits of those larger batch sizes without needing all that memory.
Okay, so it's like taking smaller bites, but still getting the same amount of like nutritional value.
Exactly. And interviewers, might ask you to explain how it works and why it's so helpful in those situations where your resources are really constrained.
Got it. Gradient accumulation.
Yeah.
Making the most of what we've got. Now, what about gradient checkpointing? So is this like saving our progress as we go?
Yeah, you're getting it. Gradient checkpointing is all about saving memory, but during the training process. So it strategically stores and recomputes activations while training is happening, so you can train larger models or use larger batch sizes without running out of memory.
Okay, so it's like taking breaks on a long hike.
Yeah.
You stop to catch your breath and have some water.
Exactly. And an interview question might be to explain the differences between these four. Momentum, mixed precision, gradient accumulation, and gradient checkpointing. Some might be faster, some might use less memory, and the best choice really depends on the problem you're trying to solve.
Right. So it's like picking the right tool for the job. That makes a lot of sense. Okay, now let's switch gears and talk about a problem that every data scientist dreads. Overfitting. Is that where the model basically memorizes the training data? And then when it sees new data, it's like, whoa, what is this?
Yeah, that's a great way to put it. Overfitting is like a student who only studies the practice exam and then they completely fail the real test because they haven't actually learned the concepts, right?
Yikes. So how do we prevent our models from becoming those overachieving test crammers?
Well, that's where regularization and loss functions come in.
Okay.
These are kind of like the secret weapons that can help our models generalize better to new data.
Okay, tell me more about these secret weapons.
Okay, so let's start with label smoothing. This one's a little bit counterintuitive, but it involves intentionally making the model a little bit less confident in its predictions.
Okay.
And this helps the model to not get too fixated on the training data, and it encourages it to learn more general patterns.
So it's like we're saying, hey, don't get too cocky. There's more to life than just this training data.
Exactly. And in an interview, they might ask how label smoothing can prevent overfitting or how it impacts the model's prediction.
Okay, got it. Label smoothing keeps our model humble. Now, what about focal loss? Does that mean the model is like focusing on something specific?
Yeah, you got it. So focal loss is amazing when you're working with imbalanced data sets. These are data sets where some classes are much more common than others. So imagine you're trying to train a model to detect these rare diseases. Focal loss can actually help the model pay more attention to those rare cases by kind of downweighting the loss from the common ones.
So it's like telling the model, hey, pay attention. These rare diseases are really important. Don't get distracted by all the common colds.
Exactly. And interviewers love to ask about this,
Yeah.
especially for things like, fraud detection or medical diagnosis.
Makes sense. Now, how would that come up in an interview?
An interviewer might ask you to explain how focal loss addresses class imbalance, or how it compares to other techniques like oversampling or undersampling.
Okay, so focal loss must know for imbalanced data sets. Now, what about drop block? Does that mean we are, like, literally dropping something from the model?
We are. Drop block is a regularization technique, but it's specific to convolutional neural networks,
Yep.
which are often used for image recognition. It works by randomly dropping out entire blocks of features during training. And this forces the network to learn more robust and general features.
So it's like training the model to see the bigger picture, even if some parts of the image are missing. That's cool.
Exactly. And interviewers might ask you to compare drop block with other regularization techniques like dropout and, highlight those key differences and when you would use one over the other.
Got it. Drop block, a cool tool for making our models more robust. Now,
Huh.
I've always wondered, what's going on inside a neural network? Is it just like a big black box, or is there some logic to all the madness?
Well, it's definitely not a black box. Even these complex neural networks, they are all trying to achieve something quite simple, and it's called linear separability. Imagine you have all these data points scattered on a graph,
Okay.
and you want to draw a straight line that can separate those points into different categories. That's basically what linear separability is.
Okay, that makes sense. But real-world data is usually much more messy than that. It's not always nice, neat, organized points.
You're exactly right, and that's why we need nonlinear activation functions. So these functions allow the network to basically transform the data into this higher dimensional space where it can become linearly separable. It's like taking this tangled up ball of yarn and untangling it so that you can see all the individual strands.
Ooh, that's a great visual. So the neural network is untangling that data so we can actually like draw those lines to
hmm
separate the categories. Now, how would this come up in an interview?
An interviewer might ask you why we need these nonlinear activation functions. What they're really looking for is to see if you understand how they contribute to the model's ability to learn those complex patterns.
Okay, got it. It's not just building the model, but understanding what's happening inside. Now, speaking of building models, I know data handling is like super important, but sometimes it feels like the boring part before the main event. Why should we spend so much time worrying about stuff like shuffling the data?
Yeah, that's a great question. Proper data handling can really make or break your model's performance. Like shuffling data. If your data is ordered in a specific way, all the cat pictures and then all the dog pictures, it can really mess with your model's learning process. So shuffling it just randomizes everything. And it makes sure that the model learns from a variety of examples.
So it's like making sure the model doesn't get stuck seeing the same things over and over again.
Exactly.
Now, how would this come up in an interview?
They might ask you about the importance of data shuffling, or they might ask how you would handle a data set that's not randomly ordered.
Okay, got it. It's all about setting the stage for that model training. Now, what about knowledge distillation? That sounds like we're making some kind of data potion.
I like that. Knowledge distillation is all about compressing those larger models into smaller, more efficient ones. You can think of it like taking all the knowledge from a wise old professor and distilling it into this concise study guide.
Ah, so it's like making the model more compact and efficient
Ex-
without sacrificing accuracy. I
yeah,
can see that being really useful, especially when you're deploying models on devices with like limited resources.
exactly.
I bet interviewers would love to hear about that.
They might ask you about the benefits of compressing the models, different techniques involved, and that trade-off between the size and the performance.
Got it. Knowledge distillation. It's must know for anybody that's interested in, actually deploying those models. Now
Mhm.
let's talk about getting the models out into the real world. Model deployment. What are some of the things we need to think about when we're actually deploying a model?
So model deployment is all about taking those models that we trained and making them accessible to users or to other systems. And this often involves creating APIs, application programming interfaces that allow others to interact with our models. So, imagine you've built a model that predicts customer churn.
Okay.
You could create an API that allows other applications to actually send that customer data to your model and get back churn predictions.
So it's like we're creating a service that others can use, but it's powered by our model.
Exactly. And interviewers love to ask about this.
Yeah? I bet they do.
They might ask you about different ways to deploy models or the challenges involved and how to make sure that the deployed model is still performing well out in the real world.
Okay, got it. It's like
Yeah,
taking it out of the lab and putting it into practice.
exactly.
Now, what about A/B testing and Canary deployment? Are those just fancy terms for testing our models?
Yeah, you got it. So A/B testing is a way to compare different versions of a model or even a system to see which one's performing better. You can think about it like running a scientific experiment.
Okay.
Canary deployment is a way to slowly roll out a new model to just a small group of users, and then you gradually release it to everyone else. It's like dipping your toe in the water before jumping all the way in.
It's a good approach.
Yeah.
So how might these concepts come up in an interview?
Interviewers might ask you to describe how you would deploy a model to production. Or they might ask about your experience with A/B testing, or Canary deployments.
Makes sense. It's not just about building it, but it's getting it out there and doing it in a responsible way. Now let's switch gears a little bit and talk about something that's often overlooked in all the excitement of building the fancy models.
Yeah.
Statistics.
You're right. Statistics is really the foundation of data science.
Uh-huh.
It helps us understand and interpret the patterns that we see.
Okay. So what are some of the key statistical concepts that aspiring data scientists should know? I bet interviewers ask about this stuff all the time.
All the time. Understanding those concepts is crucial for building good models. Let's start with the basics. Independent and dependent variables. So the independent variable, that's the factor that we think might influence the outcome. And the dependent variable, that's the outcome itself.
Okay, so if we're trying to predict, like, ice cream sales, the temperature outside would be the independent variable, and the number of cones sold would be the dependent.
Exactly. Now, sometimes there are hidden factors that can kind of mess with that relationship. We call these confounding variables.
Okay.
So imagine we see this strong correlation between ice cream sales and crime rates. Does that mean ice cream causes crime? Probably not.
Probably not.
There's probably something else going on, maybe like hot weather,
Okay.
which could lead to both increased ice cream sales and, maybe more people are out and about, so there's more crime.
So it's like a sneaky third wheel that's messing up our relationship between the variables.
Yeah, and in an interview, they might give you a scenario and ask you to identify potential confounding variables or, explain how you might actually control for them.
Got it. It's like being a data detective, always looking for clues. Now, what about stationary variables? Those sound a little more stable.
They are. Stationary variables are those whose statistical properties don't change over time. So think about, like, stock prices. If the average price and the volatility of the stock stay relatively consistent, that's a stationary variable.
So it's like a data point that's not just like bouncing all over the place. Now, why is that important?
Well, because a lot of time series models, which are used to analyze data collected over time, assume that the data is stationary.
Okay,
And if it's not, you might get these weird results.
got it. It's all about making sure the data fits the model. Now, what about interaction effects? Those sound kind of interesting.
Yeah, so interaction effects happen when the effect of one variable on the outcome, it actually depends on the value of another variable. Imagine we are studying the effectiveness of, like, a new drug. We might find that the drug is more effective for women than it is for men.
Okay.
That's an interaction effect. The effect of the drug depends on the patient's gender.
So it's like a secret combination that unlocks a different outcome.
Mhm.
I bet interviewers like to see if you can spot those interactions.
Yeah, they love it. They might ask you to explain how they work, how to identify them in data, and how to incorporate them into your models.
Awesome. It's like understanding how variables can work together. Now let's talk about distributions. This is a concept that I think can be a little bit abstract. So what are distributions and why are they so important in data science?
So distributions are kind of like the DNA of data.
Yeah.
They tell us about the shape, the spread, and the central tendency of our data.
Just like a fingerprint.
Exactly. And understanding distributions is key. It's key for choosing the right statistical tests, building those models, and just interpreting our results accurately.
Got it. Okay. So distributions, the foundation of our data analysis. Now, are there certain distributions that are like super important in data science?
There are. And interviewers definitely want to know about them, like the normal distribution. This one's famous. It's also known as the bell curve.
Okay, the bell curve. Yeah, yeah.
You see this all the time in nature, like heights and weights, test scores.
So it's a data superstar. Why is it so important?
Well, because lots of statistical models and tests assume that the data actually follows a normal distribution. So if it doesn't, we might need to transform the data. or just choose different techniques.
So the normal distribution is like the gold standard.
Yeah.
Now, what about some of the other ones? Are there any that are particularly useful for, specific types of data?
Oh, yeah. So for count data, like the number of customers that visit a store, you might use the Poisson distribution. It helps us understand the probability of these different numbers of events that happen in a specific time period.
So it's like a data clock, just ticking away.
I like that. Then we have the binomial distribution. This one's perfect for analyzing binary outcomes, like heads or tails. It helps us calculate the probability of getting a certain number of successes, but in a fixed number of trials.
Okay, so it's like a data coin flipper.
Exactly. And, we've only talked about a couple of distributions. There are many, many more, each with their own special properties.
It's a whole distribution universe. How do we know which one to use for a specific problem?
Right.
The interviewers like to ask that.
They do. And understanding those characteristics of the different distributions and being able to match them to the type of data you're working with, that's key. So if your data is like counting up events, Poisson's a good place to start. If it's proportions or probabilities, binomial might be a better fit.
So picking the right tool for the job makes sense. Now, what about feature engineering? I've heard it described as like alchemy, turning that raw data into gold.
I like that. Feature engineering is all about transforming our raw data into something that is way more meaningful and it's more informative. It's like taking raw ingredients and turning them into something delicious.
So it's about being creative and finding ways to represent the data that can help our models learn.
Exactly. And one technique that's super common is discretization. So this is where we take those continuous variables like age
Okay.
and we turn them into categories. So instead of using age as a number, you might group people into young, middle-aged, or senior.
So it's like simplifying the data,
Yeah.
but still keeping the important information. Now, how would this come up in an interview?
An interviewer might ask you, why do we discretize these variables? Or what are the different methods for doing that? And they might give you a scenario where discretization could be really useful and ask you to kind of explain your reasoning.
Got it. It's a way of making our data more digestible.
Yeah.
Now, what about feature selection? So does that mean we're like choosing our favorite features?
You could say that. Feature selection is all about picking the most relevant features for your model, the ones that are actually contributing to its predictive power. It's kind of like decluttering, getting rid of all the noise and just focusing on what matters.
Right, because too many features can really hurt. It can lead to overfitting.
Exactly. And there are tons of methods for doing feature selection. Some are super simple, like just looking at correlations. Others are more complex, like using algorithms to figure out what's most important.
So it's like a data treasure hunt.
Yeah.
Looking for those valuable features. How might this come up in an interview?
They might ask you about those different methods, how to choose the right one for a specific problem. They might even give you a scenario where you really need to do some feature selection.
Okay, got it. Feature selection is all about finding those hidden gems in our data.
Yeah.
Now let's talk about a workhorse in data science. Linear regression.
Okay.
It's a classic, right? Powerful technique for predicting a continuous outcome based on one or more predictors.
Exactly. It's like trying to find that best fit line, through a scatter plot of data points.
Right. But why is squared error the go-to loss function for linear regression? Is that just an arbitrary choice, or is there a reason for it? I feel like interviewers love to ask that.
They do. It's a great question because it shows you are thinking critically. It's not arbitrary. It's based on the assumption that those errors in our predictions are actually normally distributed.
So there is a method to the madness. Now, what about the different types of linear regression, like Poisson regression? When would we use that instead of, regular old linear regression?
So Poisson regression is a special type that we use when our target variable is a count. Imagine you're trying to predict, like, how many customers are visiting a store each day?
Okay.
The number of customers, that can only be whole numbers. And it often follows this thing called the Poisson distribution. So Poisson regression would be a much better fit than regular linear regression.
Okay, so it's like choosing the right outfit based on the occasion. We wouldn't wear a swimsuit to a wedding.
Exactly.
Now, what about zero inflated regression? That sounds a little mysterious.
Yeah, so zero inflated regression is a way of handling data sets that have a lot of zeros, more than you would typically expect. So imagine you are analyzing data on how many fish were caught by anglers. Some might catch 0 fish, which creates lots of zeros in your data set.
Right, because some people just aren't as lucky.
Exactly. Standard regression models might struggle with this type of data because they don't really know how to handle those extra zeros. Zero-inflated regression handles that. It basically combines two models, one that predicts the probability of getting a zero,
Okay.
and the other model that predicts the count for those non-zero values.
Okay, so a two-pronged attack. I bet interviewers love to see if you know how to handle those tricky situations.
They might ask you to explain when you would use it and how it differs from those standard techniques.
So zero-inflated regression, another tool for your data science tool belt.
Hmm.
Now let's talk about analyzing residuals. What are residuals and why are they so important?
So residuals, those are the differences between the actual values and the values that are predicted by our model. They're kind of like the leftovers after a meal.
Okay.
The bits of information the model couldn't quite capture.
So like the model's errors.
Exactly. And by analyzing them, we can actually learn a lot about how well our model's performing. If we see a pattern in the residuals, it could mean that the model's biased or that we're missing some important information.
So it's like a model health check.
Exactly. Now, in an interview, they might ask you to explain how to analyze residuals, what to look for, what the different patterns might mean.
Got it. We're using the leftovers to make our model even better.
Yeah.
Now let's talk about a tool that can be really helpful for analyzing these regression models, the stats models library in Python.
Yeah, stats models is amazing. It gives you this comprehensive set of tools for fitting and analyzing all those regression models, and it gives you these detailed reports.
Okay, so it's like a data scientist's best friend.
Exactly. And these reports provide valuable insights into your model's coefficients, their significance, goodness of fit measures, and lots more.
Right, because those details can really tell us a lot about how well our model is working.
Yeah.
Now, how might this come up in an interview?
They might ask you to interpret the output of one of these reports. What do the numbers actually mean? How do they relate to performance? Or they might ask you how to use stats models to actually diagnose problems and how to improve your model.
Got it. It's all about using the right tools. Now let's zoom out and talk about a bigger picture concept, generalized linear models,
Okay.
GLMs. What's the deal with these models and why are they so versatile?
So GLMs, think of them as like the expanded universe of linear regression.
Okay.
They allow us to model a much wider range of data types and relationships.
So it's like linear regression, but on steroids.
Yeah, you could say that. GLMs, they loosen up some of those strict assumptions of linear regression, so they're more flexible.
Yeah.
And they let us model things like count data, binary data, and even categorical data.
Right, because the real world is messy. It doesn't always fit into these perfect little boxes. Now, how might GLMs come up in an interview?
An interviewer might ask you to explain the concept of GLMs and how they actually differ from traditional linear regression. They might also ask you to give examples of different types of GLMs, like when would you use one over the other?
Got it. GLMs, expanding our modeling toolbox. Now let's dive into a specific type of GLM, Poisson regression.
Okay.
This is for count data, right?
Exactly. Poisson regression is perfect when our target variable is a count, like, the number of website visits or the number of cars passing by a certain point. It takes into account those special properties of count data, so it's usually much more accurate than linear regression.
It's like a custom-fit suit for count data.
I like that. And you see Poisson regression used in marketing, healthcare, and finance to model events that happen over a certain amount of time.
So it's a pretty powerful tool. Now, let's revisit zero-inflated regression. We touched on this a little earlier.
Yeah.
It's a special type of regression that's used when we have a lot of zeros in our data, right?
You got it. Zero-inflated regression is really helpful when we're dealing with data sets where our target variable has way too many zeros. Like, think about modeling the number of accidents on different roads. Some roads might have 0 accidents. That creates a lot of zeros in your data set.
Right, because some roads are just safer than others.
Exactly. And traditional models might not work so well because they don't account for those extra zeros. Zero-inflated regression to the rescue. It combines two models. One predicts the probability of seeing a zero, and the other model predicts the count for the non-zero values.
Got it. It's like tackling the problem from both angles.
Exactly. And you can use this in a lot of areas,
Okay.
like healthcare, ecology, and economics, where you see a lot of zeros.
It's a specialized tool, but it can be really useful. Now let's move on to a class of models that's known for being intuitive and powerful. Tree-based models.
Okay.
These are a great way to approach those classification and regression problems. They work by recursively partitioning the data based on different features, and it creates this tree-like structure.
Exactly. And they're so easy to understand and visualize.
So it's like a flow chart for making predictions.
Exactly. And one of the simplest is the decision tree.
Okay.
Really easy to understand, can handle both numerical and categorical data.
Okay, so it's like the building blocks for those more complex tree-based models.
Yeah.
I've also heard of random forests and boosting algorithms. What makes those different from just, a single decision tree?
So random forests and boosting, those are ensemble methods.
Oh.
They combine multiple decision trees. Imagine you're trying to make a big decision and you consult multiple experts.
Okay.
You're going to get a much better, more well-rounded perspective.
Yeah, it's like that wisdom of the crowd.
Exactly.
So how do these ensemble methods work?
Let's start with random forests. They create multiple trees by randomly sampling both the data and the features.
Okay.
So think about creating different expert teams, each with a slightly different view of the data. And that randomness helps prevent overfitting.
Ah, so it's like making sure our model doesn't get too specialized in one area.
Exactly. And to make a prediction, the random forest actually combines all of the predictions from those individual trees.
Okay, so it's like taking a vote among the trees. Now, what about boosting? How does that work?
So boosting algorithms, like AdaBoost and gradient boosting, they also combine multiple trees, but they do it sequentially.
Okay.
They start with this simple tree, and then they iteratively train more trees, with each tree trying to correct those mistakes from the previous ones.
Oh, so it's like this collaborative learning process. I bet boosting algorithms can do some pretty impressive things.
They do. They're known for their high accuracy, and they can handle complex data.
Okay, now how would these different tree-based models come up in an interview?
So interviewers love to ask about the differences between these models.
Okay.
And they might ask you to compare and contrast random forests and boosting algorithms, or explain how they handle overfitting.
Got it. So understanding those little differences is important for both putting these things into practice and for those interviews. Now let's talk about entropy. It's a concept that I think a lot of people find a bit intimidating. What exactly is entropy?
So entropy is a measure of disorder or randomness. Think about a messy room. That messy room has high entropy. Everything's just kind of scattered about. A clean room has low entropy. In decision trees, entropy is used to measure how mixed up the different classes are.
Oh, okay. So a node with high entropy is like that messy room with data from different classes all jumbled together.
Exactly. And what those decision trees are doing is they're trying to minimize entropy by finding splits that make those purest child nodes, like cleaning up that messy room.
So it's like a cleaning algorithm for our decision tree.
Exactly.
Now, speaking of cleaning things up, let's revisit overfitting.
Yeah.
How do tree-based models deal with this challenge?
So overfitting, it's like that student that memorizes the textbook. They do great on the practice test, but they bomb the real thing.
Right, because they haven't really learned the concepts.
Exactly. And, tree-based models can overfit because they can get really complex.
Okay.
So how do we stop that from happening? Well, one way is pruning.
Okay.
It's like trimming the branches of a tree, right? We can limit the depth of the tree or the number of nodes.
Okay, so we're setting boundaries.
Exactly. Another technique is regularization. This is where you add a penalty to that model's complexity, and it encourages the model to find simpler solutions that will generalize better.
Got it. So it's all about finding that balance.
Exactly.
Now, what about those ensemble methods, like random forests and boosting? Do they help with overfitting too?
Absolutely. Ensemble methods are less prone to overfitting.
Okay.
Because they combine multiple trees, and each tree has seen a different part of the data.
Okay.
So it's like getting multiple perspectives.
The power of teamwork. Okay, now let's explore a different type of learning, unsupervised learning.
Okay.
So this one sounds a little mysterious. What's the big idea behind unsupervised learning?
So unsupervised learning, you can feel about it like exploring a new city, but without a map. You have all this data,
Okay.
but there are no labels, there are no instructions telling you what to do. It's all about you discovering hidden patterns in that data.
Oh, so it's like we're data detectives, but we don't even know what we're looking for.
Exactly. And there are some really powerful techniques that we use in unsupervised learning. One category is called dimensionality reduction.
Okay.
So this is kind of like creating a simplified map of your data. Imagine you have data with tons of features, hundreds or thousands. It would be impossible to visualize. So techniques like PCA and T-SNE, these help us to project that data onto a smaller space, like 2 or 3 dimensions, but we're still keeping as much of the original information as possible.
So it's like making the data more manageable, something we can actually understand.
Exactly. And dimensionality reduction can do more than just visualize. It can actually improve the performance of our machine learning models by getting rid of noise and redundancy.
Okay, so it's like cleaning up the data, getting rid of all the stuff that's not really helping us. Now, how do those techniques, PCA and TSNE, how do they actually work? Are they kind of doing the same thing, or are they different approaches?
So they both aim to reduce dimensionality, but they use different approaches. PCA, which stands for Principal Component Analysis, it's a linear technique that finds those directions of greatest variance in your data. Think of it like finding those main streets in a city. PCA projects the data onto these main streets, and it keeps that important information.
So it's like creating a streamlined version, highlighting those most prominent features.
Exactly. Now, T-SNE, or T-distributed stochastic neighbor embedding, is nonlinear, and it focuses on keeping those local neighborhoods in the data.
Okay.
So imagine creating a map of a city, but instead of those main streets, you're focused on those relationships between, like, neighboring buildings.
So it's like zooming in on the smaller communities,
Mm-hmm.
showing how the data points are clustered together.
Exactly. T-SNE is really great for visualizing those clusters of similar data points, even when the relationships are nonlinear.
Okay, so PCA is like the map of the main roads, and
Mhm.
TSNE is like the map of the neighborhoods. How do we know which one to use?
It really depends on the data and what you are trying to do. PCA is good when you want to reduce that dimensionality, but you want to keep that overall structure. TSNE is better when you want to see those clusters of similar data points.
It's all about using the right tool for the job. Now let's move on to another exciting area of unsupervised learning, clustering. What's the basic idea, and what are some of those go-to algorithms?
So clustering is grouping similar data points together. Think about sorting laundry. You're making those piles based on color or the fabric type.
Oh.
You're looking for those natural groupings, but you don't know beforehand what those groupings might be.
Okay, so we're letting the data organize itself.
Exactly. And there are so many clustering algorithms. One of the simplest is k-means. Imagine you have all these data points and you want to group them into k-clusters.
So K just represents the number of clusters we're looking for. How does K-means actually work?
So it starts by randomly choosing k-cluster centers. Those are like your initial laundry piles. Then it assigns each data point to the closest center, and it keeps updating those centers based on the average location of the points. It's like moving your laundry pile to the center of the clothes. This happens over and over again until the centers stop moving around.
It's like a data dance.
Yeah.
Those data points are swirling around until they find their perfect partners.
I like that. K-means is pretty easy and fast, but it can be sensitive to those initial choices of where those centers are and how many clusters we choose.
Right, like if we start with the wrong number of laundry piles, we'll end up with some pretty confused clothes.
Mhm.
Are there other clustering algorithms that are a little bit better for certain types of data?
Oh, yeah, definitely. DBSCAN, density-based spatial clustering of applications with noise, is a good one. It can find clusters of any shape and can handle outliers. Think about stars in the night sky. DBSCAN can identify those dense regions that are separated by those sparser regions.
Oh, so it's like a stargazing algorithm, finding constellations in the vastness of space.
Beautiful analogy. It's a great choice when you don't know the number of clusters beforehand, or when your clusters are weirdly shaped.
So it's more flexible. Now, what about hierarchical clustering? It creates a tree-like structure, right?
Right. Hierarchical clustering builds this hierarchy of clusters, kind of like a family tree.
Yeah.
It starts with each data point as its own cluster, and then it merges the closest ones until all of the points are in one big cluster. And this creates a dendrogram, which is like a tree diagram that shows how the clusters are related.
So we're creating a data lineage,
Exactly.
showing how everything's connected.
Yeah.
How do we choose the right clustering algorithm, though? Are there rules of thumb?
It really depends. What kind of data do you have? What shape are your clusters? Do you know how many clusters you're looking for? And how are you planning on using the results?
So understand your algorithms and pick the one that fits your needs. Now, let's talk about the curse of dimensionality. That sounds a little scary. What is this curse?
So the curse of dimensionality refers to all of the challenges that come up when we're working with high-dimensional data. Imagine looking for a treasure in a small room. Shouldn't be too difficult, right?
Yeah.
Now imagine searching in this vast multi-dimensional space. It gets so much harder.
Oh, so as we add more dimensions, it's like the data gets lost.
Yeah.
It's harder to find anything meaningful.
Exactly. And this can lead to all sorts of problems, overfitting, increased complexity, and our models just don't perform as well.
So it's like our data is drowning in this sea of dimensions.
Exactly. And, dimensionality reduction techniques, those can help. PCA, T-SNE, they can help us project that data onto a lower dimensional space, and that makes it easier to find those patterns.
Okay, so it's like shrinking our search space.
Exactly.
Now, how might the curse of dimensionality come up in an interview?
They might ask you to explain what it is, how it affects machine learning, and what to do about it.
Got it. So understanding this curse and how to break it is important.
Yeah.
Now let's switch gears again and talk about data visualization. It's all about taking those boring data points and making them visually appealing and insightful.
It's like storytelling with data. A good visualization can reveal hidden patterns, communicate complex ideas, and engage your audience.
So we're making the data come alive.
Exactly. And there are just so many ways to do it. You've got the classics, bar charts, line charts, scatter plots. Those are great for trends and relationships. Then there are the more specialized ones like heat maps, tree maps, network graphs. These can reveal those complex patterns and connections.
So many options.
Mhm.
How do we choose the right one for our data?
It's all about understanding your data, your audience, and the message you want to get across. What are those key insights you want to highlight?
Right, it's about telling the story.
Yeah.
Now, how might data visualization come up in an interview?
They might ask you to describe your favorite tools or techniques. They might even give you a data set and ask you to create a visualization to highlight certain patterns.
Okay, so data visualization is turning data into something meaningful and visually engaging. Now let's talk about a skill that's basically a must-have for data science, SQL. SQL, or structured query language. It's the language of databases, right?
It is. It's how we talk to those databases to get the data, manipulate it, and analyze it.
It's like speaking the language of the data guardians.
I like that.
But isn't SQL just for those simple queries to retrieve data?
There's a lot more to it. While it's used for basic retrieval, you can also do complex calculations, transform data, even create new tables. It's like a Swiss Army knife for data.
Oh, so it's more powerful than I realized.
For sure, mastering SQL is super important, especially when you're working with huge data sets.
Now, I bet interviewers want to see if you can go beyond the simple stuff.
Yeah, they might ask you to write some really complex queries, maybe using joins, subqueries, or window functions. They might give you a specific scenario and ask you to write the most efficient query.
Got it. SQL is key. Now, let's talk about how to properly use those training, validation, and test sets. I know it seems pretty straightforward, but I feel like there are some nuances that can trip people up.
Yeah, I've heard those horror stories too. People accidentally using data from the test set and ending up with results that look amazing but then completely fall apart in the real world.
Right, it's like peeking at the answers before taking the test.
Exactly. The key is to treat your test set like this precious thing, lock it away until you're absolutely ready to evaluate your final model. Before that, you use the validation set to experiment with different models and tune those parameters. Make sure you aren't overfitting to the training data.
Okay, so the validation set is like our practice test. Now, what about cross-validation? Is that basically creating multiple training validation splits?
Yeah, that's it. Cross-validation is like running those mini experiments. It helps you to not be fooled by a lucky split and gives you a better idea of how your model will perform on new data.
So it's like getting second or third or even fourth opinions. Now, let's say we've done all of the training and validating and we're ready to test. But then, oh no, there's some new label data. Should we retrain or stick with what we have?
That's a good question. There isn't really a right answer. It depends. If you're just using that test set for the final evaluation, retraining on all of the data is usually okay. You've already seen good performance with cross-validation. But if you're using that test set for something really important, like making a big business decision, then you probably want to stick with the original model.
It's all about keeping that evaluation unbiased. Now let's talk about model interpretability.
Oh yeah, interpretability is so important, especially when you're building models that will be used for important decisions that affect people. It's not enough to just have a model that makes good predictions. You have to understand why it's making those predictions.
Right, because a black box model that just spits out answers can be a little unnerving. How do we make those models more transparent?
There are a few techniques. For linear models, look at the coefficients. For tree-based models, visualize the decision tree. And for deep learning, there are things like saliency maps and activation visualizations. It's all about seeing what's happening inside.
Now, how might model interpretability come up in an interview?
They might ask you to explain the importance of it, especially in sensitive areas like healthcare or finance. They might also ask about specific techniques for different types of models.
Got it. So being able to explain your model's decisions can really build trust. Now, speaking of trust, I've heard that evaluating model performance can be tricky, especially with imbalanced data sets. Is accuracy always the best metric?
Accuracy can be misleading, especially when you have that class imbalance, where one class is way more common. A model can get high accuracy by just predicting the majority class all the time.
Right, so it's like that weather forecaster that always predicts sunshine.
Exactly. So in those cases, you need to use other metrics like precision, recall, F1 score, and AUC.
So again, picking the right tool for the job. Now, how would these metrics come up in an interview?
They might give you that scenario, the imbalanced data set, and ask you to pick the right metric. Or they might ask you to explain the pros and cons of each.
Got it. So we've covered a lot in this deep dive. We talked about model interactions, data visualization, SQL, pretty much everything. We've seen how these concepts and tools work together so that we can get insights from data and make better decisions.
Exactly. And remember, data science is all about constantly learning and exploring.
Keep experimenting. Keep asking questions. Keep pushing the boundaries.
That's it.
And as you continue on your data science journey, always remember to approach data with a critical eye, a curious mind, and that passion for uncovering the stories hidden within.
Those are the marks of a true data scientist. Keep learning and keep pushing those boundaries.